Hi, my name is Susan Klinker and I am co-founder of Strawtegi, which is a startup natural design build company here in Salt Lake City, Utah. In addition to my background in architectural planning and design, I hold a master's degree in international development from St. Mary's and Dalhousie University in Halifax, focused on issues of shelter. I've been involved with straw bale housing in the Western United States for many years. And I join you today as a private developer to share a case study of our recent work developing a prototype zero net carbon footprint home here in Salt Lake City. The design uses a modular wall panel system insulated with chopped straw. Our purpose in developing the project is to demonstrate and contribute to the conversation about how natural carbon sequestering materials can be used in contemporary urban applications to achieve a net zero carbon footprint in a residential building shell, locking that carbon into the building shell for the lifetime of the home, and therefore serving to help mitigate climate change through how we build our built environment. Our purpose is also to explore and help validate the use of chopped straw as a high-performance, low-tech building material. To my knowledge, this is the first permitted structure of its kind in the United States that is insulated with chopped straw. I'll be going over design details, code compliance, projected thermal values, and the results of our informal fire tests. This pie chart from the United Nations Environmental Program shows almost 40% of global greenhouse gas emissions coming from our built environment. You can see the two largest segments shown in blue represent residential construction and construction industries manufacturing building materials. We know that common materials like XPS and spray foam used to achieve the important goals of net zero energy are also extremely high in embodied carbon, and they can often do more harm to the environment than good on day one before a building is ever occupied. Achieving as close to net zero carbon as possible in our new buildings and remodels has become the gold standard for sustainable design. The United Nations Environmental Program targets reduction of CO2 emissions from building materials across the industry as an immediate priority to limit the worst impacts of climate change. The Strawtegi Cottage project serves to present one way to build to achieve net zero carbon in a new structure. This home will sequester 5.5 tons more CO2 equivalents than were emitted in the production and assembly of the building shell from resource extraction to ready product. The 650 square foot structure is designed as an accessory dwelling unit, so the aesthetic design is consistent with the character of the main house. The high performance building shell is designed for long maintenance-free building life, emphasizing keeping that carbon safely sequestered inside the building shell. Passive solar orientation supports year-round comfort. High performance triple glazed solar gain windows are part of the heating system of the house. In the summer, when the sun is higher in the sky, the windows are completely shaded by overhangs and awnings, but still function to super insulate interior spaces from ambient temperatures outside. Inside, the concrete slabs provides for thermal mass and is stained with natural pigments, providing a beautiful and durable floor finish. The two-story plan includes a full stair leading to an open bedroom loft with a vaulted ceiling and space overlooking into the kitchen below. Interior finishes emphasize healthy, non-toxic natural materials like clay plaster and Tadillac lime plaster in the shower. We're also using salvaged barn material, barn wood, for the exposed beams and floor joists in the lower floor loft. Two independent single-head mini-split heat pump systems are used to heat and cool the upper and lower floors independently. We're using a super efficient electric heat pump water heater and a heat recovery ventilator system to be sure that there's adequate fresh air when windows can't be opened due to poor air quality outside. Unfortunately, here in Salt Lake, we have very poor, some of the worst air quality in the United States. All the performance specs for the equipment are shared in the paper if you'd like to know more. The key to the R30 modular wall panel system is the 7.5 inches of insulating dense pack chopped straw, which is contained in a wood fiber board structural sheathing. The Strawtegi uses 42 separate modular panels that are efficiently assembled off-site in a climate-controlled shop. The panels are then delivered and rapidly assembled on site with the support of a lift or a crane. They can also be maneuvered manually by 2 strong humans, but they're about 350 pounds, so we are choosing to use a lift in order to set them in place. The 4x8 modular wall panel system has little material waste and is friendly towards supervised limited skill sweat equity contributions during construction, which can greatly lower the labor costs. The roof assembly is insulated with Hempitexture's hemp wool batting to meet the R49 code requirement, and is finished with adorable integrated solar roof tiles by Tesla. Engineered wood shake siding by LP SmartSide provides a traditional look while drastically improving the performance and maintenance of exterior wood siding. Tongue and groove wood flooring upstairs provides a beautiful low maintenance and carbon sequestering natural floor that will patina over time. This isometric shows our 2x8 framing construction. The 1.5 inch wood fiberboard sheathing provides for structural shear, as well as a continuous thermal break on the inside and on the outside of the structure. We use 1/2 inch gypsum wallboard on the interior finish to meet fire code. The detail also shows how the panels are seated and attached to the slab. And on the second floor, interior and exterior bond beams are used to attach the panels vertically. The panel system also includes a continuous chase along the floor for electrical wiring. We use shallow electric wall boxes so that none of the electric wiring or plumbing is run through the straw portion of the wall, but remains contained in the fiberboard 1.5 inch thick interior sheathing. So the main materials responsible for the negative carbon footprint for this building shell are the sustainably forested lumber, the MSL Sonoclimate fiberboard sheathing, the locally produced cleaned and dried chopped straw insulation in the walls, the locally produced hemp wool insulation in the roof by Hempitexture, and the engineered wood siding by LP SmartSide. In these photos, you can see our process for how we manually compress the straw into the panels while they're laid flat. We use 16 cubic foot of straw per 4x8 panel, and we're able to achieve a density of 7.7 pounds of chopped straw per cubic foot. In addition, we're using natural perlite insulation to insulate the slab, which is locally mined here in Utah. We are able to significantly reduce the carbon footprint of the concrete by building in a 56-day curing time as part of our building schedule. So that allowed us to increase the fly ash content to 40% while still maintaining the structural integrity of the concrete mix. So this is one way that we could use time and supply chain delays as an intentional benefit on the project. We use the beam calculator tool from Builders for Climate Action to calculate the overall carbon footprint of our design. The beam tool is a free online emissions accounting tool specifically designed for comparing building materials side by side. So this can give architects and designers really valuable information early in the design process that can greatly improve the carbon footprint impact for their projects. In our case, you can see that the exterior walls and the cladding are responsible for the highest negative values in embodied carbon, and the concrete footings and slab are responsible for the highest numbers. During our design process, we have not found any existing lab tests measuring the thermal performance or fire resistance of chopped straw as a building material. Building authorities in Salt Lake City currently use the 2015 International Residential Code and don't require fire resistance rating for exterior wall cavities in a detached single-family dwelling. First, we conducted a basic flame test with compressed chopped straw exposed to air on all sides of an 8-inch wire column. This was really to assess our own risk for what would happen in the next larger test. We were pleased to discover that the material did not become engulfed and generally self-extinguished and smoldered rather than catching and maintaining flame while it was under compression. Moving on to the second test, we set the panel vertically and stabilized it between two adjacent steel columns. We used two 500,000 BTU propane torches set continuously for 2 hours. Along the left side, we cut away the gypsum wallboard, which we knew would provide at least a 30-minute fire resistance level of protection. So we wanted to see what would happen both with and without the gypsum wallboard. We measured 1,000 degrees Fahrenheit consistently at the center of the torch for the duration of the 2-hour test. What we observed on the left side is that it took about 30 minutes for the fire to penetrate all the way through the panel and begin to ignite the exterior face of the fiberboard. As the hole increased in size, we observed that the straw did not fall, but remained in place as charred material. This seemed to be the case even as the exterior fiberboard burned and exposed the chopped straw insulation inside. It didn't collapse or become engulfed in flames under our conditions. On the right side of the panel that was protected with drywall, the flame doesn't penetrate through to the exterior surface for the duration of our 2-hour test. The results were recorded on video for the full 2 hours, and infrared temperatures were sporadically taken on the panel surfaces throughout the test. After 2 hours, the flame was eliminated and water was applied to stop the flame spread on the exterior surfaces. But the panel was left in place to smolder for an additional 30 minutes. We then lowered the panel and removed the interior surface to visually expose what was happening on the inside of the panel. We found that the char area had spread less than 2 feet in any direction around the flame points. There was no evidence of a chimney effect rising vertically above the flame point, and there was no evidence of charred straw above an overall 4-foot height, which is the halfway point of the panel vertically. We then reattached the interior surface material and flipped the panel over and removed the exterior surface. We found similar results, except that a larger area of the straw directly adjacent to the burning fiberboard was charred, but still no charring of the straw occurred beyond a 4-foot height or the halfway point of the panel. So our informal tests serve the needs of our project, and we feel it's meaningful to share these results. But certified lab testing is needed to advance the use of chopped straw as a valid building material in the United States and under varying code requirements around the world. We are seeking support and information from anyone else who may be involved or interested in lab testing for chopped straw. In conclusion, I want to recognize our project team and the support of Builders Without Borders and the Jarvis and Constance Doctorow Foundation. The main goal of the Strawtegi Cottage project is to increase awareness and public education about the use of natural carbon sequestering building materials and to contribute to the conversation about solutions that can impact climate change in a positive way. We want to encourage a ripple effect, especially in our local community, and encourage others to explore and break through boundaries to impact climate change. Despite supply chain issues, we are now on track to complete this project in the fall of this year. We're intentionally sharing details and challenges along the way as open source information. You can keep up to date with the project or reach out to us directly through our website at www.strawtegi.org. That's STRAWTEGI.org. There is some amazing work being presented in this conference, and it's the exponential effect of so many contributions that will ultimately have an impact on climate change. I am hopeful and encouraged about so many low-tech and high-tech solutions that are advancing. It's truly an exciting time to be alive and engaged in the change. Together, we can build appropriately for the future. Thanks so much for allowing me to share our work.